Hello students, welcome back. We just completed section 1. Section 1 ended with a major theorem, which is reposted here as 2.0, of course as a review. A subgroup of a cyclic group is cyclic. Symbolically, we can rewrite like this. Start from a cyclic group generated by a certain element A and an arbitrary subgroup H from there. Then the theorem says H is also cyclic, generated by a certain element C from there. Now the question here is, of course, how do you find such C? Well, here's the answer. That generator C is actually a to the m power, where m is the smallest positive integer, so that a to that power belongs to H. This is actually a practical formula because it gives you completely algorithmic solution. Did I say completely? Well, at least almost algorithmic. Start from k equals to 1, so check A is in H. Yes, then we are through. No, then go for k equals to 2. Check if A squared is in there or not. Yes, then we are all set. No, then go for k equals to 3. Check a to the third power, fourth power, fifth power, and so on and so forth until you hit something. Finally, a to the n power belongs to H. Yes? Okay, there you go. That's how you can find the generator. As far as that process is concerned, everything is completely algorithmic. As far as checking a certain element belongs to H or not, okay, that could be a little bit complicated. So I said almost algorithmic. But in any case, I hope you see the picture. So much for the review. Now let's go to an immediate consequence of that theorem. Please recall that the set of all integers Z forms an additive group, and it's cyclic, a cyclic group generated by 1. So every subgroup is also cyclic. So that must have a generator as well, and that's got to be an integer. Let's say m. Then what do you get? A cyclic group generated by m, that's mz. So what do we have here? Every subgroup must be in this form, mz form, the set of all multiples of certain integer m. There's nothing else. Well, here's a proof, but as a matter of fact, what I just said is enough. Start from arbitrary subgroup H, then H must be cyclic too, so there got to be a certain generator M. And please recall that Z is cyclic, obtained by repeated addition of 1, or subtraction if you go backward. Likewise, get a generator M, repeated addition and repeated subtraction, cover it, and you just get MZ. So that's a proof. You have MZ and nothing else. Okay, that was easy, but let's consider a little bit more difficult application. The next topic is the greatest common divisor. Now, this is how I cover the greatest common divisor in number theory. Of course, the characters may be different, but same idea. And then you may have learned number theory from some other faculty member, and setting may be a little bit different, but idea must be pretty comparable here. What do you mean by the idea? Well, let's analyze this. Given pair of integers R and S, there is a non-negative common divisor. Non-negative, so D must be coming from whole numbers. And then common divisor, so divides R and also divides S. And of this form, the linear combination. D is an R plus MS form where M and N are integers. So basically, these three, green, blue, and red. That kind of non-negative integer exists. That's the first half of the theorem. Did I say half? No, not really. That's more than half. About 2/3, maybe 3/4 of this theorem, the existence. Now that D exists, we can consider its property First property, these are whole numbers, so greater than or equal to 0, that's clear. And it's a common divisor, so it divides R and divides S. Yeah, that too is clear. Just paraphrasing green and blue. Now this one, that's a little bit different. It's not immediately clear why this linear combination is related to this. There's another common divisor C, that is C divides R and C divides S, then C must divide D as well, and combine the fact that D is non-negative. This gives me the greatest common divisor. And this also takes care of the uniqueness as well. There's only one, the greatest number. Okay, all right. We have GCD, and of course I'm not going to prove it here. The proof was covered in one of those optional videos of lesson 3. Instead, we're going to try to accomplish the same thing in abstract algebra notation using group theory. Let's begin. Given pair of integers R and S, the set defined as follows from the subgroup. How do we define? We define it through the linear combination, red, and R plus MS form, where M and N are integers. Then we claim this set H forms a subgroup. So how do we check the subgroup? Remember that? Well, we have to check the 3 things. Close under this group operation, number 1. Number 2, the identity. Number 3, the inverse. Remember all those? Can you stop the playback and check all 3? Well, here's a sketch. Take arbitrary elements, first element, second element from this H, and then add them up. With some algebraic manipulation, we get integer times R plus integer times S, so again it's a member of H. So it's closed under addition. As for the second property, oh, that's too trivial. 0 is in there. How about the third property? Arbitrary element there, and then take a strategic element there by taking negative n and negative m, putting together, you get 0. So we have all 3 properties: closed, identity, inverse. So that's a group. That's a subgroup. It's a subgroup of a cyclic group, so it must have a generator. And let D be the non-negative generator. It must have a generator, yes. That's coming from this subgroup of a cyclic group, so it's cyclic, so it must have a generator. But then again, does it have to be non-negative? Yes, because of this observation. If D is generator, negative is also generator, because anything times D, so anything times D, A times D, A times D can be written as negative A times negative D, where A is an integer. So yes, if D is generator, negative D is also generator, and vice versa. So one of them has to be non-negative. Without loss of generality, D is non-negative, and that's it. Yes, there exists a non-negative generator. Green. So linear combination and non-negative. Okay, how about the next property there? Then, these are common divisor of R and S. Not only that, it's the greatest among them. So D divides R and D divides S. Please recall that D generates this set H. So everything here can be written as something times D. In particular, if I plug in n equals to 1 and m is 0, so if this thing just drop out and n is 1, we get r, and that's something times d, as I see from this first line. Do you see that? R is 1r plus 0s, so it belongs to this set, and that's generated by d. So R is something times d, k times d for instance, so d divides R. You can do the same thing to S. 0R plus 1s, so that belongs to this set H, the subgroup H. Now that we know it's a subgroup, so let me call it a subgroup. So this S is something times D, so D divides S. And finally, if there's another common divisor, then that common divisor divides D. So C divides R and C divides S, then C divides D as well. How to do that? Well, please note that D belongs to the set H. So D generates everything in H, but also D belongs to the set H as well. So you can rewrite it as NR plus MS form. So specific integer N0 and M0, you can write like this. So D is some NR plus MS form. In particular, we have to specify, so D is going to be N0R plus M0S. And then C divides R, so this R is something times C. C divides S, so S is something times C. You can factor the C out, and C will divide the D. Here's a sketch. So C divides R, C divides S, so R is something times C, KC. S is something times C, say JC. And then put those KC and JC here and there for this D. And what do we have? We have C common. So factor C out, then we have C times something is D. Yes, C divides D. So the conclusion. If there is any other common divisor, then C divides D. Combine the fact with this D being non-negative, D is the greatest. That also takes care of the uniqueness because there's only one biggest, the greatest. So we can finally define D as GCD of R and S because it's unique. So how did we define D? First, get this set and prove that it's a subgroup. It's a subgroup of a cyclic group, so it has a generator. And every generator has its negative version. You see, if D is generator, then negative D is also generator, so there gotta be a non-negative generator. And that is my GCD. Once you do that, then this GCD satisfies this condition, common divisor, yes, and the greatest common divisor. By the way, it's gonna be a little bit wrong to define D as GCD here because we don't know whether there's one and only one such non-negative generator here yet. But after this, yes, D has to be the greatest. So we have the uniqueness, so we can finally define it. There may be an alternative way to prove that there's only one positive D here. Oh, did I say positive? No, not really. D can be 0. The special case when R and S are both 0, then D will be 0. That's of course a singular case. One doesn't really worry about that.